Okay, now let's take a look at conservation of angular momentum. So in this exercise, we have a turntable or some sort of platform rotating around an axis through its center. So there's an axis to the center, and it's rotating around with some omega or omega naught. And we have a child standing right here at the center of it, right there. And we're told that in this condition we have there's some period. It takes 6 seconds for it to go around one revolution initially here. So our initial period is 6 seconds, and this would lead us to the initial angular speed, depending on the direction. I put it here in a positive direction. This would be, the 2 pi radians in 6 seconds. It's 2 pi radians in 6 seconds. So this is 1.047 radians per second, or pi over 3 radians per second. And we're told that the rotational inertia of the disk is equal to 1200 kilogram meters squared. And in this condition, we have the rotational inertia of the child about an axis. These are both about an axis through its center. The rotational inertia of the child about that same axis, the axis the turntable is rotating around, would be 0 because it's right there on the axis, right? And the child is a point mass here, so all the mass is right there at that point. And so then we would have our initial rotational inertia would just be the rotational inertia of the disk, which is, this is not 12 kilogram meters squared, it is 1200 kilogram meters squared, and this is 1200 kilogram meters squared as well. Okay, so this is what we have starting out, and then what happens is that the kid runs out to a point that's 2 meters from the edge. So we have a change in distribution of mass. The kid was at the center, and then the kid goes out to the edge. We can think of this as basically like a collision. We could think of it as a perfectly inelastic collision, because the kid and the turntable will have the same velocity both before and after, right? So when they have the same velocity, and the masses move together, that's like an inelastic collision. So in conservation of momentum, we look at before and after pictures, right? So this is really what's going on before. And then after, we have this turntable, and we have a child now that is 2 meters out on the edge, right? And now the rotational inertia is going to be different, right? Our moment of inertia is going to be different. Now the rotational inertia of the disk is going to be the same, right? That didn't change. The only thing that changed was the rotational inertia of the child. So now we still have I disk is still going to be this 1200 kilogram meters squared, but the rotational inertia of the child is going to be, well, since it's a point mass, this is going to be the mass of the child times the distance to the child squared, right? Which is 2 meters. And so the rotational inertia of the child now is going to be, the kid had a mass of 40 kilograms and then moves out to 2 meters away. And so this is 40 kilograms times 2 meters squared, and the new rotational inertia of the child is 160 kilogram meters squared. And so this means that the total rotational inertia now in this condition, I'll just call this I final. This is the 1200 plus 160. This is 1,360 kilogram meter squared. So the mass distribution changed, but this rotational velocity will be the same, right? So we can say, as long as there's no external torques, no net external torque acting on it, so we don't have any friction, we don't have anybody pushing on or anything like that. Actually, we have to make sure, it says, the exercise says here that the child runs out along a radius, so they actually have to run out a radial line. Otherwise, if they kind of run to the side, then that'd be like applying an external torque to the turntable. So they actually have to run out a radius, but we don't need to worry about that quite so much here. So with this, we had some initial moment of inertia, initial rotational inertia, and then we have some final rotational inertia. And from here, we can just say, all right, so we use conservation of angular momentum. This says that the initial angular momentum is equal to the final angular momentum, right? Just like we looked at in linear momentum. Conservation of linear momentum was the initial linear momentum of the system. Remember, this is the sum of all the individual momentums of all the parts, was equal to the final angular momentum so of the whole system. So we do the whole thing. We do the same thing with with angular momentum here, and so it's kind of easier because we just have the same velocity for both of these. So this is kind of more straightforward actually than the linear momentum stuff. We have the initial angular momentum as well. Write this out here. This is I initial omega initial is equal to I final omega final. And so we can say omega final is going to be equal to I initial over I final times omega initial. And before we even put this in, we should kind of think, what do we expect to happen as we distribute the mass out farther to the edge? We would expect the rotational inertia to increase, and therefore the velocity would have to decrease, right? So it should slow down. Same as when you're doing a flip off of a Rocket Waimea or something like that. In order to rotate quickly, you tuck in, and you rotate very quickly. You decrease your rotational inertia, and therefore you increase your rotational velocity. And then when you've decided that, after doing like a triple flip or something, that you want to slow down and you want to extend out and dive in, then you extend out and you stop rotating so quickly because you increase your rotational inertia, and then you would decrease your rotational velocity, right? And then you kind of stop rotating, and then you can get your bearings before you land. So applying that to this, we have our final angular velocity is equal to 1200 over 1360 times, this was pi over 3, right? And this comes out to omega final is 0.924 radians per second. And they actually didn't give us the direction here, so really we can't write it as a vector, but this is the magnitude of the angular velocity, the angular speed after. And it's slowed down, right? It was 1.047 before, and now it's slowed down a little bit, and that's exactly what we expect when we increase the rotational inertia. So basically, just treat this as a perfectly inelastic collision.